Welcome back everybody to our course on memory device technology for AI/ML computing. I'm your instructor Dr. Shubhadeep from IIT Hyderabad. Before we move forward today, let's do a quick recap of what we had covered the last time around. So in the last class we looked at how neural networks actually learn using the gradient descent and backpropagation algorithms. Remember that the cost function tells us how wrong our predictions are compared to the ground truth or the actual labels. And by calculating the gradient, what we used to do is we adjust the weights step by step in the opposite direction of the slope, thereby moving closer to the minimum error of the cost function graph. This idea of backpropagation, which is basically powered by the chain rule, lets these errors flow backward through the network. Each and every weight can be updated correctly. Once the training is over, the network then enters the inference phase. Here, new unseen data flows in the feed-forward manner through the network, and the model outputs these probabilities. For example, it classifies a particular image, as we saw, as a dog, 98%, cat, 1%, so on and so forth. Okay. And this is how trained networks then start making predictions in practice. We also surveyed some different kind of neural networks, feed-forward neural networks for basic classification and regression, convolution neural networks for image tasks, RNNs and LSTMs for sequential data like speech or text, and also generative adversarial networks for generating new data, and transformers for today's large-scale AI systems. And that was our journey last time, from learning to inference. And today we will do a deep dive into convolution neural networks. Why do we do that? Because it is one of the most widely used and efficient models, especially when it comes to doing computer vision. We will see that CNNs will not only show us why they are simpler than fully connected networks and very pervasive, but also they gives us a glimpse or a sense of how complex neural network computations have become and how wide the parameter space has also become in modern day AI/ML computing. So let us begin by understanding what is this convolution operation. You may remember from your study, especially electrical engineering students, we study convolution in signals and systems. Now, in signals and systems, this convolution operation is a fundamental mathematical operation that combines two signals to produce a third signal. And what this represents is how one signal modifies the other. And this is often described or implemented shift and multiply process, where one signal is reversed, then shifted across with the product of the overlap values integrated or summed over each step. However, in the context of neural networks, and especially when we are working with images, we adapt this idea slightly differently. Here, what we do is we slide a small filter or a kernel across the input. Now, this word kernel, new word that I'm introducing here, basically means something that it is the core or the central part of something, and we will see why it is the core or central part of the convolution operation. Now, please recall that an image that we see with our eyes looks continuous, but to a computer, it is nothing but a grid of pixel values, which is essentially a matrix of numbers. And that is how images are processed in machine learning. To make things simple, let's first start with a one-dimensional example. Now, in this one-dimensional example, instead of having an image, I have taken a 1D matrix, which is nothing but a string. So, in our case, we have an one-dimensional input string, which is 6 cross 1. There are a bunch of numbers that I have randomly taken from 0 to 14. And this, we will do a convolution operation with something called the kernel, which is a string which has dimension of 3 cross 1. So let us see how this convolution operation happens. So the convolution operation happens by three primary steps. The first step is to slide or position the kernel such that the first element of your kernel string matches the first element of your input string, as you can see in this image where I have placed them side by side. The next important step after you have placed them appropriately is to do the dot product or the multiplication operation. So what am I doing? I am doing a element wise product. So you are multiplying 14 with 1, which gives you 14, 6 with 0, which gives you 0, and 6 multiplied by minus 1, which gives you minus 6. Okay. Now coming to the third step, which is the summation of the product that are obtained. This again boils down to multiply and then accumulate. So the third step is the accumulate step, where you just simply add all these numbers that you have obtained by doing this dot product. And in this case, 14 plus 0 plus minus 6 turns out to be 8. And the first element of the output string, whose dimensions we are not yet sure of, is the number 8. How did we get it? We positioned first the kernel to have the same alignment such that the first element of the input matches that of the kernel. You do element wise multiplication and then you add them up. So this is the first step. How do we proceed next to get a string? So this is just one number, the first element of the string. To get the next element of the string, we go back to step number 1. But now what we do is we slide the kernel to the next position. So as you can see from this image, the kernel in the previous image or previous slide was such that the input of the first element of the input was aligned to the first element of the kernel. Now as you slide the kernel, what happens is that the first element of the kernel gets aligned to the second element of your input string. And what do you do next? You just repeat the multiply and accumulate operation. So in this case, you multiply 6 with 1. Remember, your kernel is not changing. Your kernel is just sliding to a new element, to the next position. So 6 into 1 multiplied gives you 6. Then 6 multiplied by 0 gives you 0. Similarly, you get minus 9. And when you sum all these things up, you get minus 3. So this is the second element of your output string. What do you do next? Obviously, you slide to the next position. And when you again do the dot product and the accumulate operation, you get a value of plus 3. And finally, you go to the last position where you again repeat the dot product and accumulate operation. Why do I say this is the final step? Because there is no other position to slide into. Why? Because if it slides into the next position, please see that this minus 1 in the kernel has nothing to get multiplied with. Since the number of elements have gotten over, that means there are no further elements that can come in the output string. So by this logic, we see that when we have an input string of 6 cross 1 and a kernel of 3 cross 1, we get an output which is 4 cross 1. Okay, so the bunch of operations that we did in the simple convolution is to first set up the kernel at an appropriate location starting from the top, such that the first element aligns with the first element, such that the first element of the kernel aligns with the first element of the input string for the first element of your output string. And for the last element of your output string, we saw that the last element of your kernel aligns with the last element of your input string. Okay, while the operation in itself is just a bunch of multiplication and addition operation. Now let me pause here and ask a very interesting question. Does the output string convey anything very important about the input string. So take a moment, think about it, pause the video and think, is the output string, which is a bunch of numbers, and just to help you out, I have color coded positive numbers I have denoted by red color and negative numbers I have denoted by this blue color. And the intensity of blue and red is indicative of the magnitude of the pixel value in that particular pixel. So does the output string convey something about the input string? Absolutely yes. Please notice carefully, the output string produced by convolving the input with this very special kernel operation 1 0 minus 1 actually conveys the edge or the gradient information about the input string or input sequence. This kernel is a special kind of kernel called the discrete derivative filter. What it does is it subtracts the value 2 steps below from the value and 2 steps above the value. So a positive output generally means that the input is increasing in this region, whereas a negative output means the input is reducing in this region. And you can see that very simply. As you go from 6 to 9, you see the value is reducing. Therefore, you get an output of -3. But when you go from 9 back to 3 or 4, you see that your value is becoming positive. It is becoming +3. With this understanding of convolution in 1D array, let's now move to an actual image. As we know, image is a 2-dimensional array of pixel values. At each grid point, you have a particular pixel value. To make matters simple and for better understanding, I have restricted the size of the input image to just 6 cross 6. So you have a grid of 6 cross 6 or 36 such pixels, and each pixel I have basically placed a value randomly between 0 to 15. Small range of values only from 0 to 15. And if you want, you can do this entire experiment or entire demonstration that I am going to show throughout in the slides by writing very simple MATLAB or Python code. So I'm just giving a very simple code that I have used in MATLAB to generate this input image. Now, what am I going to do? I'm going to try to explain what happens when this randomized set of pixel values, what happens when you take a convolution of this input image with something called the Sobel kernel. Now, the Sobel kernel has very specific meaning that we will see very soon. For introduction, I can just say that it's a very popular kernel which is used to detect horizontal edges in the x direction, and that is the meaning of this subscript gx. The first thing that we notice is that the size of the Sobel kernel is just a small 3 cross 3. So the first question that we will ask is, what will the output image look like when we take an input image of 6 cross 6 and do a convolution with a matrix which is 3 cross 3? What is the output image that is expected? And to do that, let us remember what are the 3 important rules that we performed even in 1D convolution to go from the input and kernel matrices to the output image. And the first thing that we do is the slide operation. We make sure that this kernel that we have used goes and slides into the first possible position where there are valid pixel values in the input image. So I have indicated the slide of this using this animation. As you see, it goes and first sits in the first position. So what was the second thing that we did to find convolution? The second thing was, of course, to do a element-wise dot product multiplication. So let me show you. There will be a element by element dot product multiplication. The first is 14 multiplied by -1. That is the first element. The second element is 13 multiplied by 0. That is the second element. The third one is 14 multiplied by 1, so on and so forth. So first you multiply the value of the pixel of the input image with the corresponding value in the kernel. And you do this element wise element for all the pixels within that area of interest, which I have put a red box around. Next, what was the third step? You do an accumulate. What you essentially do is the value that you get from doing the dot product, you just sum them up. And as you can see here, minus 14 plus 14 will get cancelled out, plus 6 and minus 6 will get cancelled out. What remains is just minus 12. And this forms the first element of your output image. Also, we can see that the size of the output image will be 4 cross 4. You can intuitively understand that by seeing that when your input string was 6 cross 1, Sobel kernel and kernel was 3 cross 1, what you were getting was a output image of 4 cross 1. Now you have just expanded those dimensions, so it is but natural to expect that the output image will become 4 cross 4. If you're not convinced with this argument, mentally try to slide these kernels one by one. In the next slide, we will see what will be the I plus 1th position of the sliding of this kernel, and you will see there are 4 such slides which are possible both in rows and in columns, and therefore the output image will be 4 cross 4. So let us go ahead and do the next step. So the next step to obtain the second element of your output pixel value will be to just slide your Sobel kernel to the next position. Earlier it was centered around this 1, now it is centered around this 3. So you repeat the same set of operations. First you perform a product, element wise dot product, and then you sum up all these values that you obtain from the product, and the value that you get is 7, and this forms the second element in the top row of your output image. So I will not keep repeating the same thing. It is again sliding in the third position. Now it is centered around this 10, and then you get a value of 28. And when you do it several times, when you repeat this and when you repeat this operation of sliding, multiplication and accumulation, what you essentially are able to get is the entire 4 cross 4 output image. As you saw in the animation, the first position was over here. Then first it slid through the different columns in the first row, then it went to the second row, then it went to the third row, and then finally it covered the fourth row. And this is how you generate an output image of 4 cross 4. Again, I want you to recall that these color maps have something very specific meaning. These color maps have a meaning that they are an average version of your gradient that you see in this 2-dimensional image. Let us try to understand this. You see, these regions of the output image suggest that there is a positive change, indicating that when you go from left to right, in this region of your input image, there is an increase in pixel values. Is it really the case? Of course. As you see, here there are some very low numbers, 0, 1, 10. And when you go here, you see very high numbers of 14, 15. So there is a gradual increase in the pixel values. And that is what the output image seems to be suggesting. Also, you see some large negative numbers at the bottom half of the image, and that also is quite easily visible because this part of the image has very large pixel values, 14, 15 and 13, and when you see an average across this, the pixel values seem to be diminishing. Therefore, this particular Sobel kernel is giving you through the output image an idea of the 2D derivative map. Okay. Next, I have a slide for all the computer geeks who are getting very excited looking at this algorithm and would want to do some coding. So I don't know which coding language you are most familiar with. So what I will present to you is a pseudocode. I really genuinely request you to take a moment here, pick up your computer and code a simple convolution neural network layer at least. And then slowly as we progress in the course, you can expand, you can build your own convolution neural network. So let's go over the pseudocode for this two-dimensional convolution in the simplest way. So first let's go over the initialization step. So to make things simple, I have kept the input, kernel and the output matrix to be square matrices with m cross m, k cross k for input and kernel, and you can easily see, and the size of the output matrix will be m minus k plus 1. So if you substitute the values from the previous slide, you will see m was 6, k was 3, and therefore m minus k, which is 3 plus 1 is 4. The output size was 4 cross 4. Next we do the first step, which is the slide operation. So in the slide operation, there are two loops which control this movement. So the first loop shifts the kernel down the rows and the other shifts it across the columns. At each position, what are we doing? We are extracting a small k cross k region. Remember, the box which we had was k cross k, the same size as your kernel. So this extraction of this region is also called the region of interest. Now comes the key operation, which is your multiply and accumulate operation. Here what we are doing, we are multiplying each entry in the region corresponding to the kernel. Remember, each and every element, there is an element wise multiplication. And finally, you add up all these products and this sum becomes a single number in the output matrix. So then what do? We go back to this particular step of slide because it is a for loop, and then we move the kernel one step, repeat the process and fill in the next output cell. And by the end of doing this operation, the entire output matrix is built. Next, we go ahead and see some really important concepts that are used in practical convolution neural networks. And often there is a requirement that the size of the output matrix is the same as the input matrix. Remember, in our previous examples, the size of the input matrix was 6 cross 6, but the size of the output matrix was 4 cross 4. Sometimes this is not desirable and you would want to have the size of the output image also as the same as your input image. How do you go ahead and do that? How you do it is by adding some dummy data at the edges, and this process of adding dummy data at the edges is also called zero padding, as I will illustrate in the next slide. So as you see, what I have done is this was your original matrix, 6 cross 6 matrix. What I have done is I have on either sides added a row and added a column on either sides, and therefore the 6 cross 6 matrix now with zero padding has become an 8 cross 8 matrix because I have added 1 pixel at each edge. And when we do a convolution operation with your Sobel kernel, which was just 3 cross 3, we can easily see that now the possible number of slides that are possible in both rows and columns is 6 and 6 each, 1, 2, 3, 4, 5 and 6. Therefore, by doing this zero padding, you are able to obtain an output image which is of the dimensions 6 cross 6. Now, quite contrary to the previous requirement, sometimes there is a requirement that the size of the output image be less than the input image. The size of the input image is 6 cross 6 Here you want the output image to be condensed further. You want to have it 2 cross 2. So how do we go about doing that? In order to manage that, a new concept of stride is included in the operation of the neural network. What essentially happens is the slide operation, which generally happens from one pixel to the other. Remember, the original slide operation for what we have studied till now is only moves one pixel at a time. Earlier it was centered around this, now it is centered around 3. So instead of doing that, what we do is we do a stride with length 2. So this is stride with original length 1 that I have indicated in dotted lines, and this is the stride with length 2. And you see that when we do the stride with length 2, there is no possibility of having one more slide in the x direction because there are no elements which are present over here, and as a result there are only 2 slides which are possible both in x direction and in y direction. And this is how you are able to transform a 6 cross 6 image into a much smaller 2 cross 2 image. So this is called the stride operation. And in stride operation, as you can see, some of the pixels in the image have completely gotten ignored, which is the last column and the last row. Your kernel never reaches or never operates on the values right at the edge. And this is sometimes not very desirable. So let me give you a homework problem. So in our homework problem, we have your original 6 cross 6 matrix of images. I want you to find out how you can modify the input image and include with 0 padding and also include stride length so that the 6 cross 6 image with this 3 cross 3 kernel can produce an output image which is 3 cross 3. Please think about it carefully. This is your homework task. So till now, for our understanding of convolution, we have been applying these kernels to randomized pixel values, which are almost like noise, but in reality, an image is not random. It has local homogeneities, like areas where pixel value is not changing much, and also there are local inhomogeneities where there is a sudden change at boundaries where features or edges appear. Now, this is exactly even how our brain detects and classifies these images. The visual human system is also very highly sensitive to contrast and transitions, and this is why we are able to recognize and classify shapes and objects. So how does the convolution operation that we have seen in this class helps in obtaining features from an actual image is what we will see in the next class. Along with that, we will also see how the application of convolution operation really reduces the amount of parameters and number of multiply and accumulate operations that are necessary to do useful image classification. So let us conclude today. In the next class, we will look at these 2 important points where we'll apply kernels on actual image and compute the total number of parameters that are necessary for convolution neural networks, and furthermore look at some examples of popular convolution neural networks. Thank you for your attention. See you in the next class.